All right. Hello, everyone. Welcome to this week's Crunch seminar. Our first speaker is Oliver Weeger. Oliver is an assistant professor in the mechanical engineering department at Technology University of Darmstadt in Germany. Before that, he was assistant professor in the Information Systems Technology and Design, which is an institute at the Singapore University of Technology and Design. And before then, he was a postdoc in the Digital Design and Manufacturing Center, also at Singapore University of Technology and Design. Oliver's current research interest includes computational mechanics of nonlinear solids and structures, the development of isogeometric analysis, design optimization, multiscale simulation, machine learning methods, and their applications in advanced manufacturing. So without further ado, let's welcome our first speaker, Oliver. So Oliver, you may start.
Yeah, thank you very much, Somren, for the introduction, and George for the invitation to present here today. As already mentioned, my talk is about the design of physics-guided neural networks for constitutive modeling and nonlinear multiscale simulations in mechanics. And I will explain throughout the talk what I mean with physics-guided, maybe in contrast to physics-informed, which you are all aware of. Of course, I haven't done all of this work myself. There have been a lot of contributors from my group at TU Darmstadt and from other universities in Germany, and also some recent collaborators from Spain. First of all, I'd like to give like a very brief overview of the research that my group does in general. And I'm initially an numerical mathematician, so my initial interest is in the development of new kinds of numerical methods, discretization methods, and optimization methods, like novel kinds of finite element methods. And since my postdoc time, I have been combining this with applications in advanced manufacturing, like 3D printing and also technical textiles. And now we try to combine this, of course, with physical modeling concepts, which come typically from structural and continuum mechanics. And within the last 2-3 years, we have also been looking at data-driven machine learning concepts, which we integrate basically into workflows or into complete methods that try to touch upon all of these 3 points for certain applications. And you see an overview of different things that we are doing. And I just want to mention that today the focus will be on multiscale simulation. That is basically the application in terms of numerical methods. This has a lot of applications in 3D printing and metamaterials, and also in textiles and composites, but I'm not going to talk so much about the concrete applications today, but rather about the methods themselves, where we use what I call now physics-guided machine learning, or more precisely physics-guided neural networks, in order to do modeling and simulation in continuum mechanics, and especially for multiscale simulation, and also a little bit for multiphysics. So one topic that we have been doing a lot of work in the last few years, 5 years or so, is the simulation of or the development of new kinds of simulation methods, so-called isogeometric collocation methods for 3-dimensional beams. And with these kind of methods, we can, for instance, simulate the behavior of lattice structures, like you see it on the right over here. And we can not only simulate them, we can also optimize them. So for instance, we can optimize the material distribution, the geometry in terms of the cross-section radius, the diameter, or also the shape in terms of the centerline position of such a beam or a beam structure. And then we apply this in many kinds of applications, like 3-dimensional and 4-dimensional printing of a structure that you see at the bottom here, or also for the design and simulation of metamaterials, like you see here, a unit cell of a beam-like microstructure. And we use this now also for the simulation of lattice structures and metamaterials, as already mentioned, where then during my time in Singapore, we also did experimental characterization, and we really tried to compare the simulation and the fabrication and the physical experiments with those structures. And when it comes to those structures, one thing is very apparent, which is that they are very prone to instability. So instability means that there can be buckling of the struts, like you see it over here with these parts that bend downward, or these convoluted shapes that you see in the pictures over here. This means that there's some sudden change in the behavior of the structure. And if we want to model this using an effective constitutive model for such a microstructure, this makes things very difficult. Another application that we have been working on is 3D knitting of functional textiles, where this 3D knitting is a very interesting technology that allows you basically to combine many different materials, many different kinds of yarns in different kinds of patterns together in order not only to fabricate clothes or garments, but in order to really fabricate technical composites and textiles. And there we're also interested in the multiscale simulation. These textiles, of course, they have the microstructure, which comes from the individual loops of the textile, and they have a very nonlinear behavior, very anisotropic behavior, which we try to model. So in these applications that I've just mentioned, the common theme is always that we have a microstructured material and we want to model and simulate and optimize it efficiently. So we need multi-scale simulation approaches. This applies to additively manufactured lattice structures, like I showed it, to textiles, but also to conventional composites, biocomposites, and also to biomaterials, like for instance, bone or also tissues within the human body. And there, the question is, the first question that we have is, do we have a separation of scales? Means, is there a sufficient number of these unit cells so that we can, that is not computationally feasible on one hand, in order to really resolve every beam in this microstructure and simulate it? And does this separation of scales allow us basically to look at the structure not in the complete resolution, but to look at it as a continuum? So do we need to do full-scale simulation, or can we do multi-scale simulation and multi-scale modeling? How this multi-scale modeling works in the mechanics elasticity context is that for every point in the macroscopic structure that you see on the left, basically we have a deformation and we want to get the stress for this deformation. And in order to do that, what we can do is we can regard this deformation at a certain point in the macroscopic continuum as an effective or averaged deformation of the microstructure. So the average of the deformation of this microstructure corresponds to the deformation at this point here in terms of deformation gradient in the microstructure. And that means now if we apply this deformation to the microstructure, we can compute the resulting stresses, average the stresses, and then basically we say that the stress that we have averaged, that is now the stress that we have at this point in the macroscopic continuum. And in the so-called concurrent multiscale simulation, or an FE² method, this kind of iteration would be done throughout the simulation of the macroscopic structure, but this is of course computationally very expensive. So what we want instead is a constitutive model that tells us directly what is the stress P for a given deformation gradient F. And this is exactly what we typically have, where we have a continuum material, we have a constitutive model for rubber, for metals, for whatever kind of, say, normal engineering materials we have. And it makes a difference now whether we are in the linear or in the nonlinear regime. Do we have small or large deformations? Do we have instabilities? These are all things we need to consider. We need to consider anisotropies, which means basically how does the material symmetry look like. For instance, here this microstructure has a cubic symmetry. The textiles would have some certain symmetry. Composites can have a transverse isotropy, and so on and so forth. Other effects that we might want to consider there are certain kind of uncertainties, size and localization effects, inelastic behavior when the microstructure does not behave purely elastic, but maybe viscoelastic or elastoplastic, multiphysics when the mechanical behavior is, for instance, coupled with electromagnetics, which would be the case when we have magnetic particles inside a polymer matrix. and we combine the deformation and an electric field, for instance. And then also when we can model all that, we want to optimize the structure. So for instance, we can grade the design of a structure with different kinds of microstructures. And in order to do that, as I've already mentioned, the big question is, how do we obtain the effective constitutive models? And for this, let's now just first look at the foundations of hyperelasticity, which means that the materials behave elastically, which means that the behavior is not path dependent, and it goes back to the original configuration once you release the applied deformation or applied force. So in hyperelasticity, we have a so-called stored energy function or strain energy function W, which depends on the deformation gradient F, which basically tells us what is the energy at a certain point inside the continuum. And for the thermodynamic consistency, for energy conservation, we need that the stress is equal to the gradient, the derivative of the strain energy with respect to the deformation gradient. So the deformation gradient is a 3 times 3 tensor, the stress is a 3 times 3 tensor, and the strain energy function is a scalar. Now, for the theory of elasticity, this strain energy function is subject to a lot of physical and mathematical requirements. So for instance, it should be 0 when the deformation gradient is 1, which means that there is identity, which means that there is no deformation. It should always be non-negative. It's very important that it is objective, which means that whenever you rotate the point of view on the structure, it should not have any effect on the value of the strain energy, which is this condition over here. Then we have the material symmetry, which means that when you rotate your deformation within the symmetry group, which means you rotate the material basically, this should not have any effect if you're within the symmetry group of the material. There are growth conditions and the ellipticity condition, which is a very nasty condition, because here we have this positive definiteness only for rank 1 tensors. And this ellipticity condition can be, say, simplified a little bit because it is implied by polyconvexity, which means that the strain energy function has to be convex in terms of F, the cofactor of F, and the determinant of F. So when we formulate a constitutive model, we should keep all these conditions in mind, and we should fulfill all these conditions by construction, ideally. So typically, these strain energy functions are formulated not in terms of the deformation gradient F, but because in terms of would want to be formulated in terms of the right Cauchy-Green tensor C, because in this way we automatically get objectivity, or in terms of certain invariance of C, which then allows us also to include material symmetry conditions, which we can also include using structural tensors. And typically, all of these conditions are fulfilled by the common strain energy functions that are formulated analytically, but not always the polyconvexity or ellipticity condition. But manually coming up with such a strain energy density is not trivial. There are like millions or maybe hundreds of thousands of models that have been formulated analytically, and then they need to be selected and fitted when you have certain material data. However, this is not easy when you have like very complex microstructures for which you want to determine such an effective constitutive model, because like in the case of these beam lattices, they may behave very non-linearly. They have these instabilities, which you see in this curve over here, which shows the stress that at some point there is a kink in the curve, which is due to the instability. So this kind of behavior is...
Oliver, I have a question. The
Yes.
polyconvexity, is that a physical condition or is it a mathematical condition?
It is, the polyconvexity is a mathematical condition, but ellipticity is actually also a physical condition because it relates to material stability.
So without polyconvexity, you don't have ellipticity?
Yes.
Okay. Yeah.
Okay. Yeah, so basically, since this is so difficult to get flexible constitutive models, our idea, and many others have had this idea before, is to use feed-forward neural networks because of their universal approximation capabilities in order to represent constitutive models. And in our case, we want to do this in a physics-guided way, which means ideally we want to formulate all, we want to fulfill all the conditions that I mentioned on the previous slide by construction of the model. And so far, nobody has done this before. And the first idea that we came up with is that we formulate the strain energy density W using a neural network. The neural network here is going to be the W naught over here, where we take as an input now the white Cauchy green tensor, because that gives us objectivity. And we kind of formulate around this neural network W naught a symmetrization operation that basically guarantees us the correct material symmetry. And in this way, we get a hyperelastic constitutive model that is objective, that has the right material symmetry, anisotropy, that has the flexibility that comes from using neural networks, but in this case, it does not fulfill the ellipticity. And recently, there was a preprint, I think about half a year ago, which calls this physics augmented machine learning, basically in contrast to physics informed machine learning, where here we use generators in order to include our desired properties directly into the formulation. So formulating the material model in terms of W basically gives us the hyperelasticity property, it gives us the energy conservation. Formulating it in terms of C gives us the objectivity, and the symmetrization generates the right anisotropy. And in this case, if we formulate the material model in terms of the strain energy W, then we need to be able to take the first derivative, of course, in order to compute the stress, which is what we ultimately want. But for finite elements, it needs to be twice continuously differentiable, because we need also the second derivative for the elasticity tensor. And for neural networks, this is kind of trivial, because we just have to choose the activation function as twice continuously differentiable, which is the case for many common activations functions like soft plus, the tangent hyperbolicus function, or the sigmoid function. After we had this, we were
excuse me.
Yes.
Sorry, I have a question. So my name is Henry, and I'm currently a PhD student in Professor Kanedakis group and doing similar constitutive modeling thing. So yeah, one question is, what is the G here? Maybe I have missed.
Yeah, I should have explained this. So the G is the symmetry group of the material. So if you have an isotropic material, the symmetry group is the complete SO3. If you have, for instance, the cubic symmetry, then this G is a subgroup of SO3, which I think consists of 24 rotation matrices. Okay. And depending on what kind of material symmetry you have, you basically always have a subgroup of SO3.
Okay, and for example, for isotropic material, why do you need a summation for different Qs?
Yeah, so for this approach is not very suitable for isotropic materials, because there your G is the complete SO3, which is an infinite group. So in that case, you should sort of have an integral over here. But I will talk about this also later. But okay. Here, if you have a finite symmetry group, then everything is fine. If you have an infinite symmetry group, then there's some issue, like you noticed.
Okay, okay, got it. Thank you.
I just want to make one comment, Oliver, because unfortunately I have to leave early. This is Nat Trask from Sandia. There are some networks that were published in NeurIPS. I think the paper is like 3 years old, for convexity preserving neural networks that have universal.
Yes, I'll get to this on the next slide.
Yeah, you'll get that. Okay, yeah, I just want to make sure I pointed you at it if you didn't know about it.
Okay, thank you. Yeah, so like I said, basically we're still missing this convexity or polyconvexity, and for this we can use, like you said, input convex neural networks. I'm just presenting this in this order because this is basically the order also in which we have developing the things. So we came up with two polyconvex strain energy functions. One which we formulate in terms of invariance of the deformation gradient, or rather the White-Cauchy-Green tensor, which have to be convex or polyconvex in this case. And then we can use a neural network, an input convex neural network, which simply means it is a feed-forward neural network that has some constraints on the weights and on the activation functions. So basically we have to use convex activation functions like the soft plus function. And here we use these invariants as inputs for the input convex neural network. And then here we also add some extra terms that will give us the growth condition, which is also required for the ellipticity. And in this case, basically now we fulfill all of the requirements that we want by construction. This, if we have, say, isotropic materials, then in general, the constitutive models are always formulated in terms of invariants. There are 3 invariants for isotropic materials, and using those 3 invariants, you can basically represent any constitutive model. So if you have an isotropic material, I would suggest to use this formulation because then this gives you already all the flexibility you need. If you have other kinds of symmetry groups, then it's actually not so clear how many invariants you have to use or should use and what kind of invariant. So in this case, I put the flexibility here in orange because the choice of invariants may somehow limit your flexibility. That's why we came up also with another model where we basically combine the idea from the previous slide now with the polyconvexity, meaning that we still have this symmetrization operation. And we take now an input convex neural network P of F, where we use the deformation gradient, the cofactor, and the determinant as separate inputs. This gives us the full flexibility, but in this case, we are missing the objectivity because basically it is not possible to formulate a function directly in terms of f, cof f, and det f that is objective. So in this case, in order to get the objectivity, we sort of do not physics guided or physics augmented approach, but a physics informed approach in the sense that we augment our data set. So if we have our data set, which includes deformation gradients, and for each deformation gradient, the strain energy and the stress, then we augment the data set by basically now including in the data set certain rotations from a finite subgroup of SO3. Like we mentioned before, this is an infinite group, so we cannot include all the possible rotation matrices. We can only use a finite subgroup, which we somehow have to choose in a smart way, which I will demonstrate shortly. So now let's look at the performance of these models for this application to beam lattices, where we always have this unit cell. We simulate the unit cell, we homogenize its behavior, and we do this for certain cases where we have a certain path that this deformation gradient prescribes, which in our case is always motivated basically by experiments that you can do. So as experiments, you could do a uniaxial tension test, you could do a biaxial tension test, you could do a compression test, you could do a shear test, and so on and so forth. So we have 5 cases which basically tell us how does this deformation gradient evolve, and we then numerically homogenize the behavior. We have F, we get W and P. For the calibration of the neural networks, of the weights and the biases, we use the MSE, where we use not only the MSE now in the strain energy, but also in the first Euler Kirchhoff stress. This, by some authors, this is called Sobolev training, when you do not only include the quantity that you want to learn, which is the W, but also some derivative of it. And here, basically, I just want to show the MLW model over here, which is the one that I presented earlier, that is formulated in C and is not polyconvex. And we see this actually can predict the behavior quite well. So these are all cases where we plot here the deformation gradient or the stress over the deformation gradient for the different components of the stress tensor. And we see that the dashed lines will be the data, and the continuous lines, which is the model prediction, they correspond quite well for these test cases or validation cases. However, this model is not elliptic, and this is something that we can only verify numerically. So basically we did this, we took the predictions and we computed the gradients, and we verified whether they fulfill the ellipticity condition or not numerically, and we noticed that in some range away from identity, basically it violates the ellipticity condition, and this would be not good when you do a finite element analysis, because this might lead to your nonlinear finite element analysis not to converge. Then we also tried an analytical invariant-based polyconvex model. We fitted that to the data, but this doesn't work at all in this case. In the uniaxial tension, it looks kind of okay, but in the shear cases, yeah, it cannot predict the behavior correctly. And then we also tried.
Oliver, sorry, this
yes.
data, how did you generate the data? With Abacus, how did you generate the data?
So in this case, we used like a beam simulation method that we developed ourselves, which I showed earlier at the very beginning on the slide. Basically, we modeled the microstructures as three-dimensional, nonlinear, three-dimensional beams, and then we simulate that and homogenize.
Yeah. Okay. Yeah.
So this is the standard homogenization in applied to nonlinear elasticity using nonlinear finite element codes.
Okay, thank you.
And where did I stop? Yeah, and then we have to have this the input convex neural network WI that I introduced on the previous slide, and this is also not very good in this case. So it does not have the flexibility it needs in order to represent the correct behavior, because it uses the invariants, and we don't have the guarantee that the invariants here for the cubic symmetry that they can represent all sort of behavior.
Excuse me. Hello.
Yes.
Yeah, this is Lulu from UPenn. I have one question for the results.
Yep.
So in your results, you show in some cases the accuracy is low. Can we directly improve the accuracy by increase the data set size for training? Or this is just a limitation of the model? So no matter how large the data set is, we can never get good results.
Yeah, that's a good question. I don't know whether we can improve it by using more data, because in this case, we did not have more data. And this would be the similar a similar limitation when you cannot do the numerical simulation of the microstructure, but when you can just do, say, experiments with a physical material, then you also are limited by the amount of data that you have. So I'm not sure whether more data would help here. Of course, if we have more data, then we can also use bigger networks, but actually what I will get to very soon is that we kind of want to work with as little data as possible and hope to get a model that is as small as possible. And this can actually be the case. So like you see over here, here we use now the model that is polyconvex in F, and that does not full objectivity by construction. So we do this data augmentation using a certain number of observers, like 8, 16, 32, 64, basically as the G star would have the size of 8, 16, 32, or 64 members. And then we evaluate the resulting material model after we train the neural network using about 1,000 randomly chosen rotations in SO3. And then we basically plot here the worst cases. So the worst cases would either overestimate or underestimate the true stress by quite a bit in this case. But the more observers we use, basically we converge towards, here in the case of 64 observers, something where you cannot distinguish the worst cases anymore, more or less becomes one line. So this approach works here. Using the data augmentation, we can fulfill objectivity approximately in a very accurate way. And now when we look at the fit of the data, we see here that the fit is almost perfect. So in all the cases, the uniaxial and the biaxial and the share, that would be training cases, and the mixed test over here, that is a validation case, which also has a much better prediction now even than the WC model, which say was more flexible because it did not have to fulfill the polyconvexity condition.
Oliver, doesn't this answer the previous question by Lulu? If the data augmentation works, obviously data will work. Real data will work.
Yeah, you're right.
In the limit,
yes.
Because you have to get the symmetry. Yeah.
Yes, and but actually here the interesting thing also now less data works. So basically now if we do not take the 5 cases that we had, but say we only take a uniaxial case and the share case, and we train the model, then we get almost the same accuracy as if we took the 5 cases. Of course, in all cases, we still need to do the data augmentation with 64 observers, but say the real data that we have can even become less, and we can still learn the model, which basically means the additional mathematical structure that we get from the polyconvexity improves the model, improves the accuracy, and also improves the generalization capabilities. So from this, I conclude that this additional structure is really helpful in the formulation of the model. Then we also, we were not, say, satisfied with the invariant-based model performing not so well. So we kind of went to a simpler problem now, where we used an analytical constitutive model with transverse isotropy as the symmetry group. And for this transverse isotropy group, we choose certain invariants, and then we can use a very small neural network here. This is a soft plus neural network with just one hidden layer with 8 nodes, and we can basically predict our the behavior, the model almost exactly, just using this small network, also using just a quite small amount of data. In this case, when we try to train our WF polyconvex model, then we have an issue because, like I already said earlier, thanks to the question for isotropy, transverse isotropy is an infinite symmetry group. It's not a complete SO3, but it's an infinite subset of it. So in this case, we need to do data augmentation, or we need to do not the data augmentation, but the sum for the symmetrization, also over a finite subset of the actually infinite group. So here we use now 128 rotations for the data augmentation of the objectivity, and we use 6 rotations out of the infinitely many of the material symmetry group, and we get some quite okay results, but we need a much bigger network, we need much more parameters, and the approximation is not as good as we had it here for the invariant-based model. And this raises exactly the questions that you already asked before, like how much data do we need? How much data is necessary to accurately learn a model? What can we do if we only have, say, experiments, if we have a limited amount of data? And then also very important is the question of what are the optimal sampling strategies? Like I mentioned here, we always use sampling in the F space, which is experimentally motivated, but you can also do some sort of uniform sampling. And we are currently trying to evaluate like which one is better. And so far it looks like that surprisingly not a uniform sampling is better, but this experimentally motivated sampling is actually better. But yeah, this is still a work in progress at the moment. Then we implemented these models in a multiscale simulation. So we had a nonlinear finite element code here, NetGen NG-solve, where we solved the weak form of the hyperelastic problem. We implement the constitutive models in it, and in this case, we compare the simulation of beam lattices here with 5 times 5 times 5 and 7 times 7 times 7 unit cells with the sequential multiscale simulation, where we simulate a continuum using our physics-guided neural networks. And we see a quite good agreement over here. And interestingly, if we of course, there is the incompression, the instability of the structure. And when the instability occurs after some time, also our beam model doesn't work anymore because of the instability of the buckling behavior. With the non-polyconvex, non-elliptic WC model, also the simulation doesn't converge anymore at some point, probably because the ellipticity condition is violated there. Whereas with the WF model, we could simulate the whole range that we were interested in. Of course, we still see some deviations. Here, they cannot really come from the effective constitutive model itself because that was fairly accurate. But there are other effects that can be important since our structure is not infinite that we have. There are some boundary effects, there are some size effects. And the question is, could we also include this and, for instance, use generalized continuum theories that use not only the deformation gradient, but also the gradient of the deformation gradient or some sort of micro rotation variables. And then, for instance, use also neural networks in order to fit these generalized continuum strain energies. Also, something that we are working on at the moment is basically the computational, the improvement of the implementation of these kind of methods, because of course, evaluating a neural network is fast, but is not as fast as evaluating a simple analytical model. So the question is, how do we implement this into a finite element code so that also GPU evaluation of the neural networks can be used and so on and so forth. Now, something else that we explored is the inclusion of parametric dependencies into the models. So imagine that typically, if you have a microstructure, then you not only have one instance of the microstructure, but you have sort of a family which is parameterized, for instance, in terms of a relative density or an aspect ratio, or even in terms of material properties or topological properties. So in the case of the right, you see such a cubic beam microstructure where now we basically combine three microstructures, the body-centered microstructure, which is shown in yellow, with the face-centered microstructure, which is shown in green, and the cubic microstructure, which is shown in orange. And we introduce a scaling parameter for the radius or the diameter of each of these microstructures. And in this way, we can basically combine them all together at different, with different radii. And this gives us now a family of microstructures. And we want to develop a constitutive model that can represent also this parametric dependency. Of course, if we do that, then we also need to, for the training, we need to sample also in the parameter space for the parameters, which we here take as the unit cube. But then we have to cut out basically some part, some environment around the origin, because if all parameters are zero, then you have no more microstructure, and if all are very close to zero, then your microstructure is very, very soft, and it's very difficult to simulate that, because then basically in compression instabilities occur immediately. So here we decided to do some sort of uniform sampling on the boundary of the microstructure, and then we also used some Latin hypercube sampling inside the parameter space. And for the evaluation, we then computed some points that basically have the largest distance from any point inside our training space. And a very important thing over here was that now we need to have some smart weighting strategy also for our mean squared errors. Because if you have a microstructure that basically has a parameter that is close to zero, like over here, it behaves very soft. Whereas if you have a microstructures with parameters all close to one, then it behaves very stiff. So the stresses here for the same kind of deformation case, they are like 50 times higher for the right microstructure than for the left microstructure. And if you just add this to a combined MSE, then basically the left microstructure doesn't matter anymore, because the errors you make there are negligible compared to the errors you have on the right. So here we introduced weighting with the L2 norm, where we basically always integrate over the norm of the stress along the deformation path, and then use the inverse of that to weight the error. And here we formulated the model in terms of C. So we used the non-polyconvex model because this work was done before we developed the polyconvex model. And we see that now with this weighting strategy, basically the prediction and the data, which are the dashed and the continuous lines on the left figure here, they are non-distinguishable anymore. So the prediction accuracy is quite good. And if we have such a model, then basically we can optimize microstructures and say we want to have a certain deformation stress relationship. Now please find us the parameters for the microstructure that gives this. And in this case here, the dashed lines would be the desired behavior, and then the continuous lines, this would be the microstructure that an optimization, the gradient-based optimization found that would give this behavior. Here, as I mentioned, we used the WC model, which is not polyconvex because we did this before we had the polyconvex model. But actually, we are also not 100% sure yet how to extend this approach to the polyconvex model because, yeah, I should have mentioned this on the slide somewhere. Basically, we just now formulate a neural network that takes C as an input and also P as an additional input. But it is not certain that that the parametric dependency also has to be convex. So it could be non-convex. And then if we use the input convex neural network, because we need that for the convexity with respect to the deformation gradient, then we would also enforce convexity for the parameters, which might not be necessary. So this is something we are still thinking about at the moment. Now, at the end, before I conclude, I just wanted to mention briefly some ongoing work where we are also trying to extend these models for inelastic behavior. So inelastic behavior means that there is dissipation due to rate dependencies, due to viscoelastic, plastic, or damage effects. And this is actually very important for most applications of composites and metamaterials. You want to compress them, and there will be some plastic deformation. There will be some viscoelastic behavior that dissipates energy. So if this is the case, then basically, typically constitutive models are formulated using internal variables. So in addition to the deformation gradient, now also this psi, which represents internal variables, is an input of the constitutive model. And now for the thermodynamic consistency, we need that the internal dissipation is always greater than 0. And in order to fulfill this thermodynamic consistency condition, there is a so-called generalized, how is it called? Generalized solid models, GSM, which basically state that you can relate your internal variables or the derivatives of your internal variables to certain dissipation potentials, which are called phi and phi star over here. And these potentials, they also have certain convexity conditions, they have certain symmetry conditions, which means basically we can try to transfer the approaches that we develop for hyperelastic models and for the, say, physics-guided, physics-augmented formulation of the potentials now also here to the dissipation potentials. This is what we're currently trying to do, and therefore we must take into account, of course, the time dependency. So here we have an ordinary differential equation that needs to be integrated along the way. We need to have a way how to learn the internal variables, and of course this is very much related to recurrent neural networks and the latent variables that you can have there. So here we don't have any results yet that I can show you, but I just wanted to mention that this is something we are working on. And then another topic we are working on in this direction is extension towards multi-physical behavior, and in particular electro and magnetoelasticity, which have a lot of upcoming applications, for instance, for polymers that are reinforced with magnetic particles. Then if you have such a structure, you put it in an electric field, it causes a certain deformation, like you see it in the pictures over here, which is not from our work, but from some of our collaborators. And the nice thing there is that the combination of electromagnetics with elasticity, or the electromagnetics themselves, they have very similar mathematical requirements, very similar structure to the constitutive model in elasticity. So here, for instance, we can formulate the internal energy, which is the E over here, which is the Laplace transform of the Helmholtz free energy, using the deformation gradient and using an the electric displacement field. There would also be multivariable convexity requirements. So here we need to have a convex function in terms of f, cov f, and det f, and also in terms of the displacement field d naught and f times d naught. So if we can formulate this as a input convex neural network, then we have all the mathematical guarantees that this is a properly formulated constitutive model. And of course, we can do this in terms of these, or we can then also use invariants that relate the mechanical and the electrical parts. Here we already have some first results where we used a transversely isotropic analytical electromagnetic constitutive model, generated some data, and then fitted this using a polyconvex invariant-based electromagnetic constitutive model. And you can see here that basically the dots, this would be the data, and the lines, this would be the prediction, where on top there's always the stress. And at the bottom there is the electric field E that we compute for the constitutive model. And for this quite simple case, we are quite happy with the results so far, that basically similar to the transversely isotropic elastic material, we can perfectly fit the data using quite small neural network, input convex neural network models. Okay, with this, I want to conclude my talk. So basically, we are using what I call physics-guided machine learning, or could be called physics-augmented machine learning, which also, like physics-informed machine learning methods, has the idea of introducing an inductive bias into the models using physical and mathematical structure, which can be done either through constraints or the formulation of the loss, which would be physics-informed machine learning, or using data, like we do it with the data augmentation, or using the model structure using generative properties, which would then be the physics-guided or physics-informed, physics-augmented models. And here we apply this for constitutive modeling, where we develop different kinds of hyperelastic models using feed-forward neural networks, input convex feed-forward neural networks, which worked quite successfully. We also showed that they can be applied in the multiscale simulations. We showed that parametric dependencies can also be successfully included, and that this can then be used for inverse problems for the optimization of a microstructure. Our ongoing work is in terms of inelastic behavior and electro and also magnetomechanical behavior. This is, of course, ongoing and future work. For future work, we are working on several applications. And something that we also still trying to work out better is like how, say, the kind of data, the data generation, the amount of data, the network structure in terms of the symmetrization and the inputs that we use, and the network design, say, in terms of how many layers, how many neurons, how all of these interact with also then the generalization capabilities and the accuracy, because we made the very interesting observation that once we added the polyconvexity, we also got a lot better generalization capabilities than we had before. With this, I want to thank you for your attention. I hope you enjoyed the talk, and I am, of course, open to many more questions.
Oh, George, you're muted.
Yeah, thank you, Oliver.
Thanks.
Do we have any question for our speaker?
Hi, I have one more question, Oliver. So yeah, very great talk. So I'm wondering, since as we know that in metamaterials, people can, in many situations, they can manufacture or fabricate some bistable materials, like they have two different stable states. Do you think the framework can be used to model the constitutive behavior of that kind of material, like bistable or more stable states?
Yeah, so here we have an instability in the material that we looked at, but I wouldn't really call it a bistable state. But for instance, once you have this bistability, you certainly would not have ellipticity anymore, just that your material would not fulfill this requirement. Then, depending on, say, what you want, if you want a smooth finite element simulation, it can still make sense, say, to use a polyconvex model, which then gives you the ellipticity, which you do not really have in the microstructure, but it will help you to improve the macroscopic simulation and maybe just give you one state and cannot give you the other state. But in order, say, to have this, say, switching capability between different states, I'm not sure how this could be included. Maybe with you need some sort of uncertainty parameter, or yeah, some parameter somehow that can introduce that.
Okay, yeah, thank you. Actually, it just came to my mind because your
yeah, it's a good
introduction
question.
is a metamaterial background, so it just came to my mind. Yeah, I know that there's some bistable materials. Yeah, thank you.
Hi, Oliver. This is Ming Lang. I'm a PhD student at Brown. So just to make sure, I have a quick question regarding the practicability of your proposed model, because if I'm correct, you use some sort of modified right-Cauchy green as input, and your output is energy, W, right?
It depends. Like sometimes in the non-polyconvex model, we use the right-Cauchy green as input.
Yeah.
In the other models, we either use the invariance or the deformation gradient and the cofactor and so on.
Yeah, yeah. But your output is energy, right?
Yes.
But practically, you cannot measure that if you have a new material, right? So you cannot measure energy or internal energy. But what you can get is, right, the stress. So or stretch. So that's, I think that's the best you can have. So I was wondering, like, how could you apply your model to
so this is actually not an issue at all. I'm trying to go to the slide, but I think it's very slow. So like I mentioned before, for the training, we use this Sobolev training where we include the energy and the stress in the loss function. But you can also just include the stress, and this will also work fine, actually. So we also try this, and we do not even always include the energy because learning the stress is sufficient to learn the model. And it is important basically that you include the stress in your model, in your loss function. This will help a lot and make the training be faster and improves the accuracy, but actually the value of the energy is not even important here also for the training.
Oh, yes. I agree. Because once you have the stress, you can also, another way to do this is to predict the energy, and then you calculate the stress with respect to your input. Like you do the automatic differentiation.
Yeah, that's exactly what we are doing.
Yeah. Then,
of course, we need to compute the stress, and this is done using automatic differentiation.
Yes. Thank you.
Oliver, I'm sure you know Charbel Farhat. He has a paper he showed us, because he's part of one of my projects. So he showed us like about 6 months ago a paper that has a very similar flavor with that. I think Enrui knows the paper, and they impose. Enrui, do they impose exactly the same conditions like Oliver? I know they do convexity and rotational Galilean invariance, rotations, and the application is a parachute. So they try to. They also have the RV. Yeah, they have the RV, and then they zoom in, and so they have some results. But he didn't want to put it in the archive, but I have the paper. I don't know if it was a paper published, but and Rui, you have a paper, right? I gave it to you.
Yeah, I think so. Yeah, I have it.
Yeah, I don't think I'm aware of this paper. So a few months ago, there was also a paper from a German group that also introduced the polyconvexity condition into the neural network model. And I think there was one other paper before that did this, that also wanted to include polyconvexity, but in our opinion, they did it a little bit wrongly. And then there are also some papers where they, for instance, they make the model convex, but then they make it convex in C, which is actually not what the requirement is. And convexity in C does not give ellipticity, for instance. So yeah, there are quite a few papers in the same direction.
I'm pretty sure the paper, and Henry can look it up, that did have the ellipticity condition and correlated to convexity. That's why I mentioned earlier. The other thing that we had a speaker from France, he's a good guy, Ioannis Stefanou, who presented these thermodynamic informed materials. So that's the part that you didn't show. Actually, there's a paper under review, but that paper is also on the archive. But he presented this paper here.
This is actually the same kind of approach that we are currently pursuing. Of course, we are pursuing the same that they already did, but with the slight difference that, for instance, they did not consider the convexity conditions on the potentials, as far as I know.
Right. So this is the dissipation. So this is sort of my group and other groups work on structure preserving neural networks. So there's a formulation called generic by Oettinger at ETH. So basically, we published a paper recently. I don't know if Jan is here, but he introduced generic into the formulation. So we didn't do like physics informed, was discovering actually equations from data and then imposing that. So you could integrate even stochastic dynamical systems, so systems that dissipate. So, the energy and the entropy, and you have to build these hard constraints as networks. So this is, the umbrella here is structure preserving, right? In some sense.
Yes. I think this generic framework is quite similar to the generalized standard materials framework that
it has to be. I can see that. That's the generic. I think it's more generic, but yes, it falls under that category, I think.
Yeah.
But it does pay off. That's the point. I mean, the point. Whatever system you have, mechanics or otherwise, and the soft active systems that you have, it does pay off a lot to include that. And as you demonstrated, you cut down to only 2 experiments, not 5 data sets. Yeah, and that's the bottom line. But thanks very much for taking the time today.
Yeah, thank you again for having me. It was a pleasure.
Thank you, Oliver. Okay, let's move on to our next speaker. Our second speaker is Somdatta Goswami. Somdatta is a postdoc in the Crunch group here at Brown. Before coming to Brown, she received her PhD from Bauhaus University in Germany. Somdatta and we are hosting the Crunch seminar together for this year, so I believe many of you already know her because of that. Okay, so Somdatta, you may want to take over.
Thank you. So today I would be presenting on the topic titled Over-parameterization in manifold-based surrogates and deep neural operators. This was a work that was carried out in collaboration with Katyana, who's from the Johns Hopkins University. In this work, we basically try to answer the question as to what type of surrogate models should we construct. Should it be over-parameterized, under-parameterized, or should it be deterministic? And we answer some of the conventional questions that come up normally. So the conventional thinking in machine learning, it holds the belief that by increasing the capacity of a network, it often leads to overfitting of the training data. As a result, the capacity of the model is generally controlled either by limiting the size of the data set, or they often use regularization terms in the loss function to handle the overfitting issues. However, when we talk about deep neural networks, we often see that by expanding the size of the network, we improve the generalization error, and we just improve the generalization error. And in most of these situations, we don't even require a regularization term. Now, what is this term over-parameterization? So over-parameterization is basically the term used to, the term coined so that we could, so basically it is the total number of trainable parameters of a model versus the number of data points that it has been used to train the network. Over-parameterization of deep neural network is the state of the art currently, but in this we actually study how over-parameterization helps in a deterministic and deterministic model against how it helps in a deep neural network. Over-parameterization improves the generalization in a deep neural network because it changes the loss function, and the loss function is modeled in such a way such that it results in a large number of local optimum solutions, and it helps the local searchable algorithm to look for a global optimum. Having said so many good things about over-parameterization, the main problem comes where at the training cost. So it has been shown in the literature that the training cost of an over-parameterized model is of the fourth order to its performance, and that also is stated as an underestimation. However, on the other hand, when we talk about underparameterized systems, they have limited capacity, but they are very simple, they are interpretable, and we can get these a similar kind of accuracy at a much lower training cost. Okay, so now we cannot judge the accuracy, and we cannot compare the accuracy and the complexity just by comparing the total number of trainable parameters. So what we want is to explore the expressivity of the networks, both in terms of the number of trainable parameters and the ratio between the number of data points used to train the network against the data points and against the features that it can extract. And this is what gets us to do this study, which makes us understand if and when over-parameterization helps. And this study basically focuses on the identification of an appropriate surrogate model from just a statistical point of view. In this work, we have used two kind of approaches. The first surrogate model is the manifold-based PC, and the second one is the deep neural operator. And the manifold-based PC is basically a surrogate model that is used to project high-dimensional input-output data from a mathematical model onto a low-dimensional manifold, where the interpolation can be performed for a rapid solution prediction. The manifold-based PCE involves the construction of low-dimensional embeddings of the input and the output dimension, which is an addition in the work that we did in this manuscript. And here, the conventional manifold-based PC only takes into account the lower state embeddings of the input functions. But here, for a high-dimensional output function, we also consider low embeddings for the output function. The deep neural operator, which is pretty known to most of us here, is a solution operator in which we learn the mapping of the mapping of an initial domain to its final states. And the network consists of two deep neural networks conventionally, where the branch net takes into account the functions that we want to interpret. The network has a very flexible architecture, which can have the branch net to be either a convolutional neural network or a feed-forward fully connected neural network or a recurrent neural network, to name a few. The trunk net takes the spatial and the temporal locations at which we would want the operator to evaluate the solution. Conventionally, the trunk net gives us the basis functions, and the branch net gives us the coefficients of the basis functions. And with this, we construct the solution operator. The only constraint that we place here is that the branch net or the input function at the branch net needs to be discretized at m sensor at a certain specific number of sensor locations, which we denote by m. Okay, so in this work, we have considered the Bruce-Slater diffusion reaction equation, which describes the autocatalytic chemical reaction of a reactant substance, which is denoted as A, to reach to its final substance E. Now, in this, we consider that the substance A interacts with another substance to increase its production rate. Here on the left-hand side, you can see the reaction equations of a Bruce-Slater dynamics, wherein K1, K2, K3, K1, K2, K3, they are positive parameters representing the reaction rate. The reactant substance A is converted to its final product E through in 4 steps with the help of 4 species, which is X, Y, B, and D. And it is considered that A and B are in abundance in the reaction. And we consider that they are modeled at constant concentrations. And the nonlinear PDEs representing the autocatalytic equation is shown on the right-hand side, where D0 and D1, they are the reaction diffusion coefficients. The small a in the nonlinear PDE represents the reactant substance A, capital A in the left-hand side, and similarly B represents capital B on the left-hand side. The concentration of X and Y is defined through U and V, and they are initialized through the initial conditions that is mentioned.
Somdatta, is there a mistake in the first equation? A should multiply V or something like that. The units are not right because it's a reaction constant.
Yes.
So you have to have a times a concentration.
Yes, yes.
Maybe V.
Yes.
Okay.
And also, so here we aim to learn the mapping of H2 to its H2 to its initial condition of V. But we consider that that U is a constant, and D0 and D1 are taken as 1 and 0.5 respectively, and H1 is considered to be 1. So in this work, we have considered 2 data sets. The first data set is a smooth representation of the autocatalytic equation. So the terms A and B that I described in my earlier slide, they can be modified in such a way such that we can have a smooth data set and also as a sharp data set. So smooth data set represents a stable regime in which B should be less than 1 plus A squared, and it's a fixed point analysis. So if we see here, the reaction is very smooth, and also it at a specific point, it follows a very smooth pattern, as you see here. Okay. Now constructing the data sets for training of the network. So we have used 20 snapshots for training the network, and the snapshots have been picked up from the points that has been marked here. The initial field of H2 has been modeled using a Gaussian random field, and to have multiple multiple realizations of the input stochastic field, we have used the truncated KL expansion. The data set that has been used for the training and testing is shown here, where we have used 2 out of distribution data sets. For the OOD1 that you see here, we have used a lower length scale correlation length over the training and the testing data. And for the second out of distribution, we have used a higher length scale. Now, I'll show you through numerous experiments why we did this, why we considered 2 out of distribution data. Yeah. So the results for for case 1, the first data set. Here we show that we have 16,000 total data set, total training points, and we tested on 4,000 training data. For the smooth data set, the under-parameterized, over-parameterized, depot net, and the Fourier neural net operator, they all perform considerably well. with DeepNet having the highest accuracy, the lowest error. And in the out of distribution prediction or the out of distribution generalization, we see that when we have lower length scale, the accuracy is lower compared to when we have higher length scale for the out of distribution data. And also in this experiment, we have added 10% noise, and the noisy data set also shows that DeepNet generalizes and is more robust towards addition of noise. The number of trainable parameters that each of the network uses is presented in column 3. And
hello, Somdatta. Yeah, this
yes,
is Lulu.
Yeah,
so what's on the DeepNet architecture here?
Sorry?
What's the DeepNet architecture of the branch and the trunk?
Okay, the branch net is a CNN and the trunk net is an FNN.
And what's the size? Because I only see, let's say, 100,000. Apparently, it seems to me is compared to FNO is pretty small. It's 100 times smaller than FNO.
Lulu, your voice got disrupted once again.
It's a very small compared to FNO. Right?
Yes, it's very small compared to FNO.
So, why is FNO is so large?
That even I'm not sure why FNO is. I can check it once.
Okay, yeah, thank you.
Yeah, the number of training. Yeah, I'll check it once. Okay, now in this.
Somdatta, do you have the details of the CNN?
Yes, I have. You want me to show that?
I can answer the question to Lulu.
Oh, okay. So it is 16 filters. It is three convolutional three layers of convolution with 16 filters, and the filter size is 5, and the stride is 1.
Okay, I see. So it's actually okay. It's a small CNN. It's only 3 hidden layers.
Yes. Yes.
Okay, thank you.
Okay. Yeah. In these okay. Now we performed another experiment where we wanted to understand till what extent does a discrete surrogate model can take up over-parameterization against deep neural networks. On the left-hand side, we see the over-parameterized, we see the manifold PCE, where it can be shown that if there is a modest amount of over-parameterization, the generalization accuracy improves. However, with aggressive over-parameterization, the testing accuracy and the out-of-distribution accuracy starts to deteriorate. Against DeepNet, the DeepNet accuracy keeps on improving as the total number of trainable parameters increases, but there is a small catch at the end of the network, at the end of the graph, which is beyond 1.6 times 10 to the power 5, wherein a very small regularization term had to be added to improve the accuracy. And that is what I'll show in my next slide. The vertical line that you see here on the left graph is basically the total number of parameters, the total number of training data. In this results, we show that for a large so we have kept the CNN architecture the same, and we have modified the trunknet architecture, and we have also modified the FNN beyond the CNN, the classifier part. And we show that when we change the classifier, we need a little bit of regularization to improve the accuracy. So this happens when the network size immensely increases, and the total number of trainable parameters is shown in the third column. Also, through this, we wanted to show that the accuracy of the network keeps it keeps deteriorating as we increase the amount of noise through the last 3 columns. In this, we perform a small experiment to understand what is the effect of the training data size over the accuracy of the network. So for an and here NT represents 20, which is the total number of snapshots per case. And we show that.
Hi, Sananda. Sorry, I have another question for your previous result.
Yes.
So here it shows by adding 30% noise, the accuracy is still very good. So yes, seems excellent. So how do you add noise? So is point-wise Gaussian noise or?
Yes, Gaussian noise. Point-wise Gaussian.
Okay. And for each point is independent Gaussian for each
yes.
For each pixel. Okay, I see.
Yes.
Yeah. Okay, that's great. Yes, 30%. Yeah. Awesome. Yeah. Thank you.
Okay. So now we perform this. So here we show that when we have a small training data set, the underparameterized system is more accurate over the overparameterized models. And but as the data set size increases, the overparameterized models, they start to perform much better over the underparameterized systems. But the DeepNet does a good job. DeepNet has the best accuracy when we have a very large data set. And overall, for smooth data set, all the surrogate models, they are able to efficiently capture the capture and predict the solution. And through this graph, we have represented the same information. This is the final. This is the error plot for each of the models for a specific case of a specific reference solution, which is the first row. And you have we can see the errors on the next 3 rows for DeepNet over and under parameterized models at 5 timestamps. Now the second set or the second data is in a limiting cycle where the parameter B has the parameter B is greater than 1 plus a squared. This is a very unstable regime in which the system approaches a limit cycle. So here the transition dynamics is very sharp. So we obtain a kink at certain timestamps and in this periodic timestamp. In this, we have taken 10 timestamps for training our data set. And as we see here, we have a similar study that we conducted for the previous data set. And in this, through this experiment, we also want to check if the observation that we did previously matches. So in this experiment or in this data set, we actually have used self-adaptive DeepNet or self-adaptive weights in the DeepNet because the sharp kink that we have in the solution that normally cannot be captured using having the loss function without any weights. So those weights either need to be manually updated. So we proposed using a self-adaptive weighting DeepNet. So we improved the solution from 0.16% of error in the kink area to having 0.4% to having 4% error in the kink area. The similar experiment that I previously presented with the first data set is also presented here, and the self-adaptive DeepNet is more accurate over the other data sets, and we see that when the adaptive without using the self-adaptive, if we manually modulate the error from DeepNet, we can obtain a test accuracy of 4% against the other ones. And we can also see here that the under and over-parameterized PCE models, the under-parameterized PCE model is unable to do a good prediction over the over-parameterized counterparts. Coming to a similar study with the increasing the number of data points. So the under-parameterized model, even though improves by adding data points, but still is way less accurate over the over-parameterized counterparts. And the POD DeepNet and self-adaptive DeepNet captures the information very well over the other ones. In this, we show the same error plots against against a single reference solution for the over-under parameterized PCE, DPONet, POD DPONet, and self-adaptive. And we can see that self-adaptive DPONet is more accurate for the 5 timestamps. Finally, concluding through this, we concluded the following observations. So the first one is that over-parameterization leads to a better generalization, often achieving higher and significantly higher accuracy than its under-parameterized counterparts. DPONet is very less sensitive to the trainable parameters against the manifold PCE. This could be concluded because the x-axis of DPONet was much smaller in range over the manifold PCE. And in case of smooth dynamics, both the MPC, both the manifold PCE and the DPONet, they have sufficient good accuracy. However, this accuracy in both noise and as well as the out of distribution generalization. However, this accuracy is often reduced when we have nonlinear and non-smooth dynamics. And we see that when it comes to out of distribution prediction, for a length scale which is lower than the trainable data set, lower than the data set that has been used for training, the accuracy is lower compared to if we have out of distribution data set where the correlation length is higher than the length scale that has been used for generating the training data set. And we also record the deterioration of the smooth deterioration by adding noise. And also this shows that there is the generalization error is also increasing as noise increases. And also lastly, we would like to comment on the time taken for training the network, where in manifold-based PC, it takes a few seconds to train the network. However, with DPONet, we take close to 700 times more time to train our network over manifold-based PC. And with this, I would want to conclude. Thank you.
Maybe I have one last question. So have you tried self-adaptive POD DPONet?
No, I did not try that.
Yeah, that the accuracy may be further improved.
Yeah.
Yes. Okay, I see. Thank you.
Hi, this is Ting Wei. Can I ask you a question?
Yes.
It's a very basic question about the model. Can you go back to the model? I mean, the PDE. Yeah, this one. Can you explain briefly why we have those terms on the right-hand side of the PDE, like VU square? I assume this VU square comes from the third equation on the left-hand side, right? I mean, I'm just...
Wait, these are reaction terms. So first of all, the equation is wrong. Maybe you can look up the terms from that. I think it's A times V, but I'm not. So the diffusion term you understand, and then there is like the competition of the species, right? The two species. So that's like standard ways of modeling. It's like, think of a reaction, you model it like K times U to the X power. Now, nobody knows exactly what X is. So there's like all these people who have proposed these models with different terms to account for the generation and the consumption of the different species in the reactions.
Okay. Is there any variational representation for those PDEs?
Not for the nonlinear terms.
Okay, I see. Thank you.
The nonlinear terms, yeah, and it could be arbitrary. Usually, what we're trying to do these days is to just like, that's why I say in reactive transport, you know equilibrium, but non-equilibrium reactions are never known. So these are ad hoc models. There's no actually rigorous way of deriving this. This is all postulations.
Okay.
You know, so certain models, I mean, not every model looks like that, but this particular model, the brucellator, is I think it's for catalysis, right?
Yes.
So if you cannot use this, for example, this to burn oxygen in a diesel engine where you have reactions, that's not going to work.
Okay.
And that's why you see also this AB constants. Diffusivity is fine, that's easy, but the AB constants are there to reaction parameters that nobody knows. If you do coagulation cascades like HLE, there's reactions also there. The equations look similar, just different terms. Ameya is working on a combustion problem with and Somdatta with 10 different species, I think. Yeah. The equations are like that, and you know, kinetics is basically forget about the Laplacian thing of du dt equals those terms. These are ODEs, right? System of ODEs, and then on top of that, you also have for each point is an OD, and then on top of that, you have this diffusion term, and you can have also advection term, but this one is slow, basically no flow. If you have a flow, you will need also an advection term, but the difficult part is always what you're asking: where are these terms from?
I see. Okay, thank you.
Population growth models and so on have similar type of interactions.
George, this A doesn't have a V. This is the original equation.
It cannot be, because then it's not a reaction constant. There's no the dimensional consistency.
Yes, I can also see.
So
I'll check that.
So I would call it the propagation of error somewhere. But maybe non-dimensional, because I see, but it doesn't make sense to just have a reaction constant there. I see it's normalized because we add 1 plus b. So these are but still you cannot have like that. That's impossible.
Yeah.
It will be like a source then. It's not a reaction constant.
Yes.
It will be a function of space-time.
Yeah, I will check that.
Did you explain to people what is PCE? No, but you went so fast, blazing. So you finished in 20 minutes, but I don't think you explained what a PCE is, manifold PCE.
I actually invited Katyana also for the talk for this PCE thing. I'm not sure if she's there in the audience.
Here.
Yeah, she's there.
But Katyana, you gave a talk here. Can you go back to slide 3, because Somdatta tried on purpose to go really fast through that to avoid any questions. But now we have you here. Maybe you can remind us what you presented before, how this successful method works.
Yeah, so basically the idea here is that if we have a model and we have a very high dimensional set of inputs, like some stochastic fields in the case of the brucellator, we can use practically any dimension reduction technique to identify a lower dimensional embedding. And then, so in the work that Somdatta and I did, we used kernel PCA, but different methods work best for, I guess, for different problems. And then once we have identified this embedding, and so the reason why we do this is to basically break the curse of dimensionality. And once we've done that, then we can actually map these lower dimensional inputs to our outputs. And in this case, we have used polynomial chaos expansion.
That's the PCE, yeah.
That's the PCE, which is the polynomial approximation. So basically, the PCE allows us to expand our mapping into a set of polynomials times some coefficients. We can use different methods to compute these coefficients. Yeah, basically in our paper, we have proposed an extension of this method where we also perform a dimension reduction on the outputs, because we have this field that evolves in space and time. And so we basically perform 2 separate dimension reductions. We identify the 2 lower dimensional embeddings, and then we construct a PCE surrogate between those. But the caveat here is that for the dimension reduction of the output, we need to be able to have an inverse mapping so that we can go back to the original space when we want to perform out of sample prediction, let's say. Yeah, so that's the main idea. I'm sure Professor Kniadakis is an expert to talk about the PC method in general. But that's the, let's say, the variant of the method is the manifold part, where we map, reduce basically data that live on these latent spaces.
And Katiana, can you also say what were the dimensionality, the dimensionality of the embedding?
Right. So for
in the two cases, yeah.
Yeah. So
I'll go ahead and send.
Yeah, so for the inputs, we have fields that are 784 dimensional, and then we reduce that to 18 for the under-parameterized case and to 30 for the over-parameterized case. And then you can see in the output in the second column of this table, you can see the reduced dimensionality of the output. Of course, we need to basically try to optimize that, so find which are the optimal dimensions both for the input and output. So here we have done that in a grid search manner, basically. So we have found that these work best for this set of data generated by the Brusselator model.
Could one use encoders to accomplish that?
Yes, yes. So in a survey paper that we also published recently, we posted on arXiv, we tried to do autoencoders, both the vanilla version of it and then like a variant, the Wasserstein autoencoders, which uses the Wasserstein distance. And it can work well in certain problems. We have used it on a similar problem to Brusselator. So yeah, you can use any dimension reduction technique.
Yeah, that's good. Yeah, Great.
Do we have any more questions?
I think the unanswered question is what Lulu said. Go back to the 30% noise. Usually with 10% noise, that's kind of the limit. To go to 30% noise, and it seems that all this is you're showing here the. Did you subject also the manifold PCE in this noise? Did you check?
No, this result is only for the DNN. I think we have the result, but we did not put it up for the manifold.
But it performs similarly. In other words, the results are still bounded. The error is bounded like that, because 30% noise is a lot. So, and this is case 1 or case 2?
This is case 1.
Case 1 is easy. I think that's right. I think case 1 is easy. Case 2, just to answer Lulu's question, I think case 2 the error would be large. So you may want to check that, because it looks too good to be true.
Okay, for the case 2 also we'll do that.
30% noise, you can just get out of any trap in the energy, so you can go to the bifurcation. So it may be that this dissipates destroys the noise very quickly, and also the fact that you have the regularization term.
And also, George, we have a CNN. So in the trunk, no, that in the branch.
No, because in the other paper with Lulu, we show that the CNN actually doesn't like noise. Right, Lulu? Remember the instability, the wave instability?
Yes, we tried this auto encoder decoder type CNN for the wave problem, and the noise, the accuracy actually really bad for large noise for CNN.
Okay, I'll try it for the case 2 for the data set 2, and I'll check what happens with 30% noise.
For both models, for both surrogates. That's an important. Actually, let's focus on that. Anybody else? We haven't submitted the paper yet, so if you ask difficult questions, actually you will help us, because we want this to be a quick review.
About maybe a small question. Have you observed the double descent for DeepNet?
Again?
The double descent for DeepNet.
No.
And
not for this case, right? Yeah, you know what he's asking about?
Yes.
Okay. Yeah, what you show in the beginning, kind of.
Yeah, exactly.
Okay, yeah.
It's very, as you know, Lulu, you tried to do that. It's very difficult to find real systems. Double set. It's only for these academic problems that the people who wrote the PNS paper it appears.
Yes, yes. The real problem is really complicated and it's not easy to get it. Yeah.
Yes, Somdatta, this is Raj.
Yes, Raj.
I have a question. Can you go on the previous slide?
Yeah.
No, there where you mentioned the error between DeepNet and 2% error in the DeepNet for this. Here, for your test data, there is a 7% standard deviation, and for 10% noise, you have a less standard deviation, 2%. Is it usual? It should be more.
But this is what we got actually, Raj. Yeah.
That is fine, Miss. But is it like you generally observe? But in my experience, like it should be the standard deviation should be more. If you are adding 10% noise.
Yeah, I agree with unless you change the regularization, there's something fishy.
Yes.
With your noisy data.
Yes, I will check it.
What kind of noise it is? Like
maybe pink noise, not white noise.
No, pink. White noise.
Yeah, so the testing data for clean data is worse than the noise data.
Yeah. No, this noise is added in the so the training data, we added noise in the training data and we checked it.
Okay.
No, yes, go ahead, Lily. But in the usually when we add noise, so your standard deviation go more actually.
So Raj, actually, this is what I mean, Lulu just now pointed this out. So basically, this noise that I tested on is on the data that I have used for training. In that, I have added noise and I have tested it. So I guess that is the reason which explains why I have so less standard deviation.
So this is noise on the training data, not on the testing data.
Yes, exactly.
But then the testing data is clean.
The testing data is clean, yes.
Oh, so then it makes sense because you learn better from perturbations of the data. We know that.
Yes.
So we're talking about different things. To check the mappings, if they're stable, you actually want to put. I mean, this is fine. This is what you did is fine, but that we know enhances learning. To test the stability of the mappings, you need to put noise on the testing data.
Okay, I'll do it. Yeah.
Lulu, this is what we did in our paper, right?
Yes, the stability. Yeah.
Because that's the only way to actually check, and maybe you can try both, even for Katjana's model. You want to add noise. I think even 5% noise will be too much, I think. But what you have demonstrated here, it would be nice to see all the data, is that something that people know that if you add noise, because to the data, it's like data augmentation, actually.
Yes.
This is called Gaussian. There's exactly data augmentation technique we use with Ishan in her paper. So we added Gaussian noise, and you get better results. So that's no surprise there, Raj.
Okay.
It's on the training. Yeah.
Yeah. So because it's not from testing, that is it.
I don't think in reduced order models, Katjana, because people are afraid of noise in general. So I don't think they actually use noise in training. So it would be interesting also for you to check that actually noise in the training, it enhances accuracy, and then noise in the testing checks the stability of the embedding. Basically, the embedding that you learn, how stable it is.
Mm-hmm. Yeah, I don't usually see this study in manifold-based papers. So yeah, we should do that.
Yeah, because diffusion maps, I know they really, Yanis doesn't like noise on diffusion maps. He wants them as clean as possible, okay? So that's the reason. They have now techniques that they deal with it, but...
Lulu, I forgot, what was the first suggestion that you gave me? Which you wanted me to check. One, I already took the 5% noise on the test data. The other suggestion that you just now, you previously mentioned, which I mentioned I would be checking.
The number of parameters or FO is 100 larger than DeepNet.
Yeah, that's a good point, because there's an easy way to beat the FNO is actually to use a CNN on instead of FNN. But if it's from data only. If it's physics informed, then you cannot use that. But for data only, a CNN, if you have regular data, will always beat FNO if you use CNN on the branch. Okay, thank you all. Thanks for the yeah, we need to do a little more work then on this paper, and then we can submit it. Yeah. Okay. Thanks, Katiana. Thanks for dialing in.
Thank you.
All right. Thanks very much, everybody.
Okay, everyone has a good weekend. See you.